Today, I am Trisha Dela Cruz, one of the members of Group 2, and I will going to discuss the introduction about the chemical reaction called Oxidation-Reduction reaction. There are countless of chemical reactions. Since they are well known, it is helpful to categorize them into classes or categorize so that we can deal with them systematically, and this can lessen the confusion for us. Chemical reaction in further detail classify them as oxidation-reduction reaction, combination reaction, decomposition reaction, displacement reactions, gas formation reaction, and metathesis reaction. The last type can be further described as precipitation reaction and acid-base neutralization reaction. However, we will going to focus only on oxidation-reduction reaction since it is our topic for this video. Oxidation-reduction reaction is a reaction in which oxidation and reduction occur, and this is also known as redox reaction. We can observe that this reaction fit into more than one category and that some reactions do not fit neatly into any of them. As we go on, the term oxidation originally referred to the combination of a substance with oxygen. This results in an increase in the oxidation state of an element in a substance. Oxidation is an increase in oxidation state and correspond to the loss of electron. Oxidation state is a formal concept adapted for our convenience. The number are determined by relying on rules. This can result in a fractional oxidation state. According to the original definition, the following reaction involve oxidation of the substance shown far on the left of each equation. Oxidation state are shown for one atom of the indicated kind. For example, the formation of NaCl or the sodium chloride, where we add Na, which is sodium, and Cl, which is chlorine. As both Na and Cl have no charge, as these are electrically neutral atoms, they need to have it to attract to form the sodium chloride. And to make them both have charge, sodium needs to give one of its electrons to chlorine, and this is where oxidation takes part. As per the definition before, oxidation happened to the left part of the equation. In this case, the left part of the equation is Na or the sodium, so we will do oxidation in this part. Sodium now lose its one electron and have a charge of a positive or a +1 for it to lose one electron, as in charge of an element, plus indicates a minus and the minus indicates an addition. Now that we have done discussing oxidation and we have now a one lost electron, where the one electron went now. Reduction is a decrease in oxidation state and correspond to the gain or apparent gain of electrons. Originally, reduction is described as the removal of oxygen from a compound. Oxide auras are reduced to a metal, which is a very real reduction in mass. Back from the example before, we are now have one electron from Na. We are now putting it into chlorine by the use of reduction. Reduction happened at the right part of the equation, and in this case, chlorine is located at the right part, and this is the element that will gain one loss of electron from sodium. Chlorine now has a negative or a -1 charge, indicates an addition. Now that both Na and Cl have an opposite charge, they will now attract and form the sodium chloride, as we know that opposite charge attract. As we are done discussing the oxidation-reduction reaction, you can now look for other examples like the ones shown in this picture. And to sum things up and have a simple definition, remember that oxidation is a loss of electron and reduction is a gain of electron. Oxidation happened to the left side of the equation while the reduction happened to the right side of the equation. Thank you for listening. Now that we are done discussing the introduction about the oxidation-reduction reaction, we are now having a further discussion of it that will be discussed by Miss Ivory Constantino.
Hi everyone, I am Ivory Ann M Constantino, one of the members of Group 2. In this video, I will discuss the important part of our topic. Now that you know the difference between oxidation and reduction, you must also be reminded that sometimes the terms oxidation number and oxidation state are often used interchangeably, so you must be careful to use the appropriate word. Oxidation number in simple terms can be described as the number that is allocated to elements in a chemical combination. The oxidation number is basically the count of electrons that atoms in a molecule can share. Those are gained while forming chemical bonds with the other atoms of a different element. Oxidation number is also referred to as oxidation state. However, sometimes these terms can have a different meaning depending on whatever we are considering the electronegativity of the atoms or not. The oxidation number term is used frequently in coordination chemistry. In general, oxidation state or number help us describe the transfer of electrons. However, you have to note that it is different from a formal charge which determines the arrangement of atoms. The oxidation number or state is also used to determine the changes that occur in redox reactions. Meanwhile, it is quite similar to valence electrons. Electrons are neither created nor destroyed in chemical reactions, so oxidation and reduction always occur simultaneously and to the same extent in ordinary chemical reactions. In the four equations cited previously as examples of oxidation, the oxidation states of iron and carbon atoms increase as they are oxidized. In each case, oxygen is reduced as its oxidation state decreases from 0 to 22. So now, for you to have a deeper understanding in oxidation, let me show you another example of oxidation and how does it form. Oxidation and reduction reactions are always interlinked because electrons are neither created nor destroyed in a chemical reaction. Oxidation and reduction always occurs in pairs. It is impossible to have one without the other. In the below reactions, magnesium gets oxidized by losing 2 electrons to oxygen, which gets reduced by accepting 2 electrons from magnesium. Because oxidation and reduction occur simultaneously in all of these reactions, they are referred to as oxidation-reduction reactions. For brevity, we usually call them redox reactions. Redox reactions occur in nearly every area of chemistry and biochemistry. We need to be able to identify oxidizing agents and reducing agents, and to balance oxidation-reduction reaction. Oxidizing agent gains electrons and is reduced in chemical reaction. A reducing agent loses electrons and is oxidized in a chemical reaction. Oxidizing agent, also known as the electron acceptor, and reducing agent is also known as the electron donor. In oxidation state, oxidizing agent decreases while reducing agent increases. Examples of oxidizing agents: halogens, potassium nitrate, and nitric acid. Halogens, they favor gaining an electron to obtain a noble gas configuration. Examples of reducing agent: the earth metals, formic acid, and the sulfate compound. Alkali metals, they favor losing an electron to obtain a noble gas configuration. These skills are necessary for the study of electrochemistry. Electrochemistry involves electron transfer between physically separated oxidizing and reducing agents, and interconversion between chemical energy and electrical energy. These skills are fundamental to the study of biology, biochemistry, environmental science, and material science.
Hello, my name is Axel Onia, and I am here to discuss the oxidizing agents, reducing agents, and how the equation of redox reaction can be written. Okay, so now that you have learned from the previous discussion the difference between the oxidizing agents and reducing agents from the reporter earlier, let's now classify how we can differentiate each of them. Now let's talk first about the oxidizing agents. These are the species that oxidize other substances. They also contain atoms that are reduced and gain or appear to gain electrons. Next, second one is the reducing agents. These are species that reduce other substances, contain atoms that are oxidized, and lose or appear to lose electrons. Okay, so the following equations represent examples of redox reactions. Oxidation states are shown above the formulas, and oxidizing and reducing agents are indicated. So, this is my first example. As you can see here, the oxidation state of iron is 0, and the oxidation state of chlorine is also 0. For the iron, the oxidation state is increased by +3. Oxidation has occurred in iron because it went up. Now, chlorine has reduced. Notice that the oxidation number has decreased from 0 to -1. So therefore, it was reduced. The oxidized is also known as the reducing agent, and the substance that reduces is also known as the oxidizing agent. Why is in that case? The reducing agent is the substance that causes the other element to be reduced, so the iron is considered as the reducing agent because it causes chlorine to be reduced. Next example for more understanding. As you can see here that iron charge doesn't change, so you don't have to worry about it. Notice that bromine is increased from -1 to 0, and chlorine is decreased from 0 to -1. So therefore, bromine is oxidized and chlorine is reduced. Simple tip here is to make sure to reverse it to get the correct answer. So therefore, bromine is the reducing agent and chlorine is the oxidizing agent. Equations for redox reaction can also be written as total ionic and net ionic equations. For example, let's use the previous example, the equation before. The second equation may also be written as, take a look at the picture. So next is, we distinguish between oxidation states and real ion charges by designating oxidation numbers as -n or +n in circles just above the symbols of the elements, and actual charges as n+ or n- above and to the right of formulas of ions. The spectator ions, Fe3+, do not participate in electron transfer. Their cancellation allows us to focus on the oxidizing agent, Cl2, and the reducing agent, Br2. Next is the proportionation reaction. Take a look at the picture. This proportionation reaction is essentially a form of redox reaction where the same elements of atoms are simultaneously reduced and oxidized from oxidation state to two separate oxidation states. In essence, a molecule with an intermediate oxidation state is split into two new compounds with higher and lower oxidation states. Thus, a species undergoes simultaneous reduction and oxidation to produce two distinct products. So, take a look at my next example. Here is a hydrogen peroxide. Here, oxygen experiences this proportionation, so the oxygen of peroxide present in the -1 state gets converted to the 0 oxidation state in O2, and at the same time decreases to the -2 oxidation state in H2O. So, oxidation cannot occur without reduction and vice versa. An oxidizing agent in chemical reaction is reduced, while reducing agent is oxidized. This can be very confusing, so take some extra time to understand these important relationships. Here's a simple tip to fully understand and recognize redox reaction. You can always recognize a redox reaction by analyzing oxidation states. By examining oxidation states, a redox process may always be identified. Every element that appears in the reaction should first have its oxidation state determined. The reaction is not an oxidation-reduction reaction if the oxidation states of the components remain unchanged. If modifications do take place, the reaction is an oxidation-reduction one. Keep in mind that oxidation and reduction always go hand in hand. If one element's oxidation state increases, another must decrease.
Hi everyone, my name is April Dapon and I am a member of Group 2, and I will report my part, and that is all about the corrosion, and this is the experiment that we've done, and also this is some aspect of corrosion. Corrosion is a chemical or electrochemical attack on the surface of the metal. Since our experiments would involve around it, then we can say that our experiment is indeed a corrosion and sample of oxidation reduction. Reaction is one of my co-member also discusses what the real meaning of it. The most common example of corrosion is the rusting of iron. In a redox reaction, the site where reduction occurs is referred to as the cathode, and the site where oxidation occurs is referred to as anode. Before that, let's recall on our mind that the cathode is the positive or oxidizing electrode that acquires electrons from the external circuit and is reduced during the electrochemical reactions. The anode is the negative or reducing electrode that releases electrons to the external circuit and oxidizes during the electrochemical reaction. And also, right now, the objective of our experiment is to observe that the electrochemical nature of the changes is an iron nail when it corrodes, and to investigate methods to protect it. In these experiments, the corrosion of iron will be observed, and we can say that this happens because the incorporation of a more oxidizable metal and combination of iron is done and seen as a way by which the corrosion of iron is presented. Incorporation of a less oxidizable metal, and on the other hand, enhances the rate of corrosion of iron. And of course, to start our experiment, we must first have our apparatus and also a material. And yep, this will be using on. However, since our prof tell us that we're not doing it literally without him, as our in-person supervision, let's just assume first and imagine it in our mind. And of course, let's not okay, this is the things that we need to prepare. Of course, the 250 ml beakers and also zinc materials. Let's not forget the copper wire, and also 4 clean 1.5 and ungalvanized clean iron nails, And also let's have the 0.1 MK3FE or CN6 materials, and also the 1% phenolphthalein, and also distilled water, pliers, sandpapers, and 2 small jars.
Hello, my name is Cindy Parumog from Group 2 and I am here to report to you the continuation of our experiment corrosion with its connection to our topic chemical reaction under oxidation reduction. So to start our experiment, we must follow the proper procedures or steps to have a better outcome. First, let's assume that our instructor assigned someone to prepare for our gelatin. And to start with our procedure, we must boil about 250 ml distilled water and able to prepare the gelatin solution. Stir into the boiling 1/2 bar colorless gelatin. Heat the mixture with continuous stirring until the gelatin is well dispersed. Set aside until the temperature solution reaches 60 degrees Celsius. Add 20 drops of K3FeCN6 or our potassium hexacyanoferrate, Roman numerals number 3 into the solution and stir thoroughly. Add 1.0 ml of 1% phenolphthalein into the cooled and unsolidified solution before pouring into the prepared jars. So, while the gelatin solution is being prepared, sand the nails to remove the surface coating, then prepare 2 jars according to the following setup. So, imagine, for example, we have jar A and jar B. Jar A with respective nails, we will place it as nail 1 into the straight, and nail 2 bent to a 45-degree angle using a pair of pliers. While on jar B, the respective nail number 3 is to be with a clean cloth piece of bare copper wire twisted around it, and nail number 4 with a piece of Moses zinc forced through the nail. After doing so, we are expected to place the nails side by side at the bottom of the jar, making sure that the nails do not touch each other. Pour the gelatin into solution into the prepared jars, taking care that the nails and metals are covered to a depth of at least 1.0 cm. During that experience of experiment, we are expected to observe the nails in the jar toward the end of the lab period. Make a properly labeled diagram of your setup and indicate the colors that develop around each nail. This is one of the important things we must do to avoid problem with our experiment. Bring the jars home to make further observation, but this will only apply for those in-person lab experiment. After that, of course, every lab experiment has a waste disposal, since this is a very important to also avoid conflict in the future. And however, since we don't have in-person instructor, let's assume that waste disposal is being done so. So waste disposal number 1, carefully remove the Moses zinc and copper wire from the nails and rinse this well with running tap water and return to your instructor. Waste disposal number 2, dispose all nails used in the experiment into the used nails container provided by your instructor. Waste disposal number 3, dispose used gelatin in the solid waste container. So now, have you imagined our experiment? Now with that experiment, let's also answer the questions that we might encounter. So question number 1, what do the blue ends in the straight nail represents? The indicator color changes suggest that oxidation and reduction occur at the different sites on the nail, and the blue areas indicate that the presence of iron 2 oxide or Fe2+ ions happen due to the oxidation of iron atoms. Our question number 2, what does the pink coloration in the gelatin solution indicate? Well, our answer is the pink area coloration means it's going to form a rust, because let's remember that hydroxide ions are produced before rust is formed. Question number 3, compare the results of the nail in the beaker A to those in beaker B. So in beaker A, our question is, how does the copper wire affect the corrosion of iron nail? The copper wire has the opposite effect on the iron. With iron being a better reductant than copper, electrons are pushed into the copper and a pink color is seen around that metal. So in Beaker B, explain the effect of the zinc metal on the corrosion of iron nail. Well, our answer is that zinc gives up its electron more easily than iron, so it preferentially gives electron to the oxygen and also pushes electron toward the iron, making the iron less likely to corrode.
That's it. Thank you for listening, and we hope that you learned something from the Group 2 whole presentation report and can now differentiate the difference between oxidation reduction from any other chemical reaction.